Hello everyone, this is Maurizio, editor-in-chief of Power Electronics News and Embedded.com. I am at Electronica, showing in Munich, and I have the pleasure to be here at Fraunhofer booth with Michael Mensing, head of Group Advanced Devices at Fraunhofer. Hi Michael, thanks a lot for being here. How's it going?
Thank you for having me. I'm wonderful. It's a great fair to have interactions with our customers and all our collaborators.
Yeah, indeed. So we are at Electronica. Before starting, I have prepared some questions for you. So tell me more about you, your job, and Fraunhofer, of course.
Okay. Fraunhofer is a great society. We have over 80 institutes all throughout Germany with our extended offices throughout Europe and the world. Myself, I'm the head of the Advanced Devices Group at Fraunhofer Institute for Silicon Technology. We are located a bit north of Hamburg in Itzehoe. In principle, we are focusing on gallium nitride-based power electronics and also emerging into the fields of gallium nitride-based MEMS and sensor technologies nowadays. And at the same time, we're looking into the next generation of what can we do with gallium nitride beyond these kind of discrete devices, looking into ICs, memory technologies based on GaN, and looking where this is taking us in the next few years.
Great. So we are at Electronica. A lot of companies are showcasing innovations. So what is innovation for you? So tell us more about innovation from Fraunhofer point of view.
From the Fraunhofer point of view, we are excited that the developments are going into a more electrified society, and as well the age of AI, if not in the last couple of years, is now definitely arriving. We see AI methods being used throughout the different stages of the systems, from raw data processing up to the applications in the end. And the different components that are enabling these kind of innovations are the memory technologies, and as well a better understanding on what are these application areas missing and where the different edges can be refined in terms of AI-based innovations.
So let's talk about the famous pilot line. So Leti and Fraunhofer are expanding the collaboration on energy efficiency memory technology. So tell us more about this collaboration, some news, some next.
The FAMES or Farmers pilot line is a really exciting showcase of how R&D institutes throughout Europe can cooperate and innovate together. The idea is that basically we take the strengths of the different R&D institutes and unify our initiatives into a better Europe. And the idea behind FAMES and the cooperation with Fraunhofer in this area is especially focused on non-volatile memories, so mostly ferroelectric-based field effect transistors based on FDSOI technologies, but also some emerging memories that are lying beyond this in the next couple of years. And in the exciting way, actually, Fraunhofer will have a proposal that's supposed to be concluded in the next, let's say, 2 weeks or so. That is a Fraunhofer or a FMD-based pilot line like FAMES with the CA Leti colleagues, where we have the interaction exactly the other way around. Our pilot line, Apex, as the promo behind you is showing, is focusing on the heterointegration of these things and basically building complex systems that are application ready from the individual components and strengthening the interaction between the different components, making everything more efficient and as well faster time to the market. And this is the part where these two pilot lines can interact most and also benefit the European ecosystem in the near future.
Great. So Fraunhofer is also working in terms of power electronics, and one topic that I'm also spreading the voice is wide bandgap, gallium nitride and silicon carbide. So a comment about these new it's not so new, these technologies in different applications. How can they improve and solve the current limitation of power electronics?
So let's start out with silicon carbide. I think that's the most widely familiar material system at the moment. Silicon carbide transistors that you can buy nowadays to power your traction inverters and whatnot are mostly based on planar technologies. Here we are basically talking what we had in the silicon technologies 20, 30, 40 years ago, and now we see how a similar roadmap of these more advanced devices will be brought into life in the next few years. And similarly, the same might be said for gallium nitride as well. Here we have our first drastic change in terms of semiconductor development by the invention of the HEMT, so high electron mobility transistor in the last couple of years, where device physics are completely different. There's still a lot to learn in terms of reliability and application knowledge of these devices. We haven't really seen how far we can take these devices yet. And looking ahead also in terms of bringing gallium nitride to the same robustness of these other semiconductor materials, where we can see that gallium nitride-based CMOS technologies are emerging. We have seen exciting announcements in the last couple of years and projects with respect to vertical gallium nitride, which might be a replacement of even higher power levels for silicon carbide at the time. And we basically now have the race to the market where we try to bring our own perspective into these kind of innovations.
So wide band gap, but what about ultra wide band gap? What about gallium oxide?
Gallium oxide is very interesting because of a couple of different topics. It's definitely, in theory, better than gallium nitride and or silicon carbide. From our perspective, the most challenge will be how far we can advance the field of power electronics by utilizing a gallium oxide, for example, when we start out with completely developed silicon carbide or gallium nitride-based devices. I think industry expects a larger improvement over gallium oxide, for example, going in the direction of aluminum nitride or even carbon-based devices, to reason the investment that needs to be made. At the same time, it's a very exciting time that nowadays even gallium nitride is emerging into larger areas of production. So we have 300 millimeter announcements in the last couple of weeks from German companies as well. And the issue for emerging ultra-wide bandgap materials will be the question on who is supposed to fabricate these when we are running out of 4 or 6 inch commercial fabrication areas. And what kind of technologies do we need to scale up these ultra-wide bandgaps? My personal investment there is going into the direction of emerging substrates or heteroepitaxial approaches to basically bridge the gap directly into commercialization, but there are still a lot of kinks that need to be ironed out, and that's where we try to make our part.
So let's talk about the intelligence within the power module. So AI and power electronics. So what advancement we can expect in integrating the real-time control, data monitoring within the power module in different applications. So I can mention energy, for example, in general, but not only.
Power let's say power electronics and AI, or speaking in our Fraunhofer branding and cognitive power electronics, is an exciting innovation that we will see more and more so in the next couple of years. We already have intelligent power modules on the market, and I think these will evolve even further to the point where we expect our inverters in the next few years to be able to tell us, hey, in your B6 configuration, the transistor on the top right will break down in a couple of days. You should maybe look into buying a new system, or at least avoid a short outage of your production environment. And that's going further beyond understanding how your devices and your packages are failing, also into the device physics itself. And the idea is how can we basically create a digital twin of our power electronics, including the applications that are sitting behind, so motors, and even going up to grid applications, where we try to get a better understanding on how these different systems play together on drastically different levels, basically on the very low component level. We're talking electrons that are being moved around and semiconductors that are maybe degrading over time. And on the other hand, we have large machines that are moving, and these kind of systems are interacting. So we can learn a lot of how does the system behave, and what does it tell us about the individual semiconductor, and vice versa. And these innovations we will see more so, and that should lead us into at least a more reliable future of power electronics. And also it might be a chance for wide bandgap and ultra wide bandgap emerging devices to enter the market faster, even though if their reliability might still be lacking a bit, but at least you can tell us you need to buy a new one or replace your system anytime soon, and that way gain more acceptance in the market to new technologies.
So Michael, this is great information. And so my last question, looking at the future, so which is your comment, key message, but in particular, collaboration between industry, academics, these are important. So how do you see, how do you envision the collaboration, maybe also in terms of wideband gap, in terms of artificial intelligence or in general? So tell me your comment.
Yeah. Speaking a bit in general, Fraunhofer has the challenge to support our industry that we see in Germany, Europe, or the entire world, and we try to accelerate their innovations. So basically, the idea is if we found a Fraunhofer Institute, we always have the requirement to have local industry that we would like to support and to enable into doing R&D within Europe and not looking to R&D centers around the world. And the system on how industry and Fraunhofer can collaborate spans the entire value chain. We can evaluate machines that they would like to introduce in the system. We can free up some space in their manufacturing by transitioning some of the R&D activities into our own facilities and help basically make everything run a bit smoother on their end. And at the same time, an external view doesn't hinder these developments. And sometimes we have also the role of where we bring people together that otherwise haven't collaborated in the past. So where we can create projects on national or international scale and basically take over the management part and help these different companies to find a common language.
Great, and looking forward to it. Thank you, Michael. Thanks a lot for your time.
Thank you very much. Take care.
Thank you.